finally we have come to the last exercise. So in this exercise, you see, okay, let me just read what the exercise says. The purpose of this exercise is to show that there is essentially only one version of the natural number system in set theory. What it means is that if you go back to some of the discussions that we had after we introduced the system of natural numbers, there you will see a remark, specifically this remark 2.1.12, where we have said that using piano axioms we can introduce the natural numbers. That is only one of the ways, one of the possible ways of introducing this system. You can also use cardinalities of finite sets to introduce them. So it's like having different different names for the same person. The different names do not change the person. The person behind those names is the same. So it's like that the system of natural numbers actually is something that is not changed by the way you introduce it or you construct it. You either use Peano's axiom or you use some other method. It does not matter. So in this exercise we have to show that. Also, it is language independent. So if I have, say for example, our ordinary system of natural numbers, the way we have developed them, and I use some other symbols in some other language, say in my mother tongue Bengali, I can use Bengali numerals. The underlying mathematics will not change, provided my new system or the other system also satisfies Peano axioms and all those things. Okay, so specifically we have to show this. Suppose we have a set n prime of alternative natural numbers, some other system of natural numbers, an alternative 0 and an alternative increment operation which takes any alternative natural number n prime and gives another alternative natural number, its alternative successor if you will, such that this new system also satisfies the Peano axioms with all the natural numbers 0 and increment replaced by their alternative counterparts. Then we have to show that there is a bijective mapping, a bijection F between n and n prime that maps the 0 of our ordinary natural number system onto the alternative 0. Also, if we have two elements, one ordinary natural number and one alternative natural number, they correspond to each other. That is, specifically n prime is the f image of n if and only if this happens. That is, the successors also correspond to the successor of n corresponds to the successor of n prime in the alternative universe or alternative natural number system. Okay, so if you want to see what that means, we have already seen this, so I am rubbing this part off. I anyway need this space. It's like having these two systems. Say I have our ordinary natural numbers and I have, say, these other symbols. Okay. In Bengali we write 1, 2, 3 like this. Shunno, ek, dui, tin, etc. We say like that. So what this exercise asks us to show is that there is a bijection between these two sets such that the 0 of our natural number system corresponds to the 0 of the other system, and if these two things are corresponding to each other, then their successors, this is the 2 is the successor of 1 in the ordinary system, and Dewey is the successor of 1 in the new system. So this is equal to this, and 2 is equal to, then they also correspond to each other, that is these two are corresponding to each other, and this is true for any such any pair of ordinary natural number and alternative natural number that correspond to each other. If they correspond, their successors have to correspond, and conversely. Okay, so this is what we have to show. So let us see how we can show, and the hint says that we have to use the previous exercise, and this is why we had that general version of proposition 2112, which otherwise is also known as the principle of recursive definition. We need it here. So let us see how the solution can be written. Consider the function we are going to consider a function g from this set into the set of alternative natural numbers given by this formula g of m comma n prime. Keep in mind, m is an ordinary natural number and n prime is an alternative natural number. This is equal to the successor of n prime in the alternative natural number system. So this function is well defined. Why is it well defined? Okay, I feel I should write something about why this function g is well defined. Since the alternative natural numbers or I should write number system so that everything is included in it, not just the elements but the alternative increment operation and everything else, satisfies the piano axioms G is well defined. And why is that true? That is because you see, if you take any the image after all is not depending on m, although m is there, it is depending on this alternative natural number n prime. So when we are given an alternative natural number, then there exists an alternative successor, and this is nothing but axiom 2.2, if you remember, second piano axiom, that is also satisfied by this new system. So from there we are getting the fact that G is well defined. Okay. So now look at the structure of G. G is a function of the type n cross a set A, where A is this set of alternative natural numbers into the set A. So we are in a position to use the general version that we mentioned in the solution to the previous exercise, and that's what we are going to do exactly. With in place of C we are going to take 0 prime, sorry. So because C now has to belong to this set, so by the remarks in the last part of the previous solution, where by previous solution we mean the solution to the previous exercise. There exists a unique function f from n into n prime such that f of 0 is equal to c. Now c we have chosen to be the alternative 0 that we can choose. Okay, c can be chosen to be any element from this set, and f of n plus plus is equal to g of n comma f of n. For all n belonging to n. So this is, we are getting this from the previous solution, but we have a specific definition for g. So according to that definition we will get something. Hence for all n belonging to n we have this is equal to what will it be if you look at this? This is the alternative successor of fn. So that means please don't forget the distinction between ordinary successor and alternative successor. For an ordinary natural number n, we can have only an ordinary successor, which is also an ordinary natural number. For an alternative natural number fn, because f is a function from n into n prime, so fn is here. For that we can only have an alternative successor, which is again an element in n prime, that is, it's an alternative natural number. Okay, so note that one of the requirements that we have, f of 0 equal to 0 prime, is already there. Now we have to prove that if we have a natural number n and an alternative natural number n prime, then f of n is equal to n prime if and only if this happens. This is one of the things we have to prove. The other thing we have to prove is that f is bijective. F has to be both one-to-one and onto. Okay, so we will do these things one by one. So let us first note that we already have f of 0 equal to 0 prime, alternative 0. Also, if n is a natural number and n prime is an alternative natural number such that fn is equal to n prime, then we have, okay, then what do we have from here? Directly from this equation we have fn plus plus is equal to n prime plus plus prime. So one part of that equivalence is already available to us. I mean, it's an easy consequence. The converse have to be proved, but before proving the converse is just that if we have this and this such that this is true, then this is true. That is the converse. So before we prove that, let us just prove that f is bijective, because we need that in the converse somehow. Let us now show that f is first let us show that f is surjective or onto. For this we apply induction, but we have to be careful what we are actually doing. You will realize what I mean by that. Let us start the process. We have 0 prime is equal to f of 0. So basically what we are going to do here to show that f is onto is that we are going to choose each element, each alternative natural number, and show that that is the image of some ordinary natural number. That we will do by induction on the alternative natural number. That is, if we have an alternative natural number, say n prime, then we have to show that there is a natural number n whose f image is n prime, and on that n prime we are applying induction. So our base case is there for us already. Okay, assume that for some n prime belonging to n, there exists n prime belonging to n prime, there exists a natural number such that f of, let me just follow the same pattern of writing, n prime is equal to f of n. That is, we have assumed that some alternative natural number n prime is the image of some natural number, is the image of something, some natural number n. Then okay, then by what we have proved here, you see, if this happens, then this happens. Then n prime, the alternative successor of n prime is equal to this, which is equal to, from here, which we have already proved. Keep in mind here what we have proved. If this is true, then this is true. So we have this true, or according to our induction hypothesis, whatever we are assuming here is the induction hypothesis. So this is true, and this is nothing but f of n plus plus. So the assumption that the alternative natural number n prime is the image of some natural number leads us to the conclusion that its alternative successor is also the image of some natural number. So this actually completes the induction. But induction where, that you have to be careful about. Induction in the alternative natural number system, not in the ordinary natural number system. So instead of writing induction, we will write it like this. Since n prime satisfies the fifth piano axiom, which is actually the axiom of induction, that is true for n prime, and that's why whatever we are going to say in this case using induction, that will be true. The above arguments show that for every natural number, since I have used n prime here, let me just use something else. M prime belonging to every alternative natural number m prime, there exists some ordinary natural number m such that f of m is equal to m prime, and this clearly shows that f is onto or surjective. So f is surjective. Now next we prove something that will imply that f is injective. Next we prove the following. For any n and m belonging to n, if n is less than m, these are ordinary natural numbers, if n is less than m, then f of n is less than, alternative less than f of m. Here this is the relation, or I should say ordered relation, although we have not seen what a general ordered relation means, but just for the sake of saying, we are saying this is an ordered relation. In chapter 8 we will see what a general ordered relation is. Okay, so this is an ordered relation, that ordered relation in the alternative natural number system that corresponds to the relation in this. And keep in mind, whatever we have developed, whatever theory, all the theorems, all the results that we have developed in this system, they have exact counterparts in this system also. So the properties of ordinary ordered relation, they are also true. I mean, similar properties are also true for this new relation, and this we are going to prove. And this again we are going to prove by induction. we prove this by, and this induction is going to be ordinary induction because it is something that depends on this ordinary natural number. So it's going to happen in this system N by induction on M keeping N fixed. N can be any natural number, but we are which is arbitrary but fixed, but M is going to be the variable on which we are going to induct. Note that so the first case or the base case appears when M is 0. Note that the implication N less than 0 implies f of N less than f of 0 is vacuously true. Okay, so this is vacuously true. Why? N is a natural number, and from properties of natural numbers we know that no natural number is less than 0. 0 is the smallest natural number. This, if you go back to the properties of order relation, when we first defined it and then proved its elementary properties, there we will find this. Okay, so in this implication the hypothesis is false, so the implication is vacuously true. It's true nonetheless. So this is the basis for our induction. This is the basis for our induction. Now assume our induction hypothesis. We are now going to assume that for some natural number m and that arbitrarily fixed value of n, we have, if n is less than m, then f of n is less than f of m. Let, so now next part we have to prove. We have to prove a similar implication where in place of m we have its successor, because then only that will complete the induction. So the hypothesis of that implication should be this: if n and m prime are such, it's not m prime, it's the successor of m. If we have this, then we need this where m is replaced by m plus plus. Then okay, so if n is less than the successor of m, then two cases arise. Then either n is less than m or n is equal to m, because n being less than m plus plus means it is less than or equal to m. So either it is strictly less than m or it is equal to m. If n is strictly less than m, then by our induction hypothesis, then by the induction hypothesis, we have fn is less than Fm, okay, and okay, we need m plus plus here, so this is equal to, how can we have Fm plus, oh yes, yeah, now I understand it, and this is less than Fm, the successor of Fm. You see, we already know that every natural number or alternative natural number, since they will have identical properties, is strictly less than its successor. That has also been proved at some point after introducing this order relation. We have already proved that before. So we are using that in the alternative system to conclude that this alternative natural number Fm is less than its alternative successor. But according to what we already have, from our previous relations that we have seen in this solution, this is nothing but f of m plus plus. I hope what I have written is correct. Let me just see what I have written here is correct or not. Yes. And in support of this, we can write the properties of the relations this and the alternative one are identical. Okay. So you see that here we have what we need. If n is less than m plus plus, then we have got f of n less than, alternative less than fm plus plus. But that is under the condition that n is less than m. When we have n equal to m, if n is equal to m, then I don't think we have to do anything. Then f of n is equal to f of m, which again is less than f of m plus plus, and that is nothing but f of m plus plus. So if, or let us write like this, since after all we are mentioning it as an implication or writing it as an implication, so here also the conclusion should also be as an implication. So we have implies this completes the current induction. And proves our claim, that is, if we have n less